Okay, so in this tutorial, what we're going to look at is elevator problems. Elevator problems are related to Newton's third law, related to Newton's second law, and also related to Newton's first law. They're incredibly important to understand, and they're going to help us also understand the normal force a little bit better. So we've got Alpha the alligator, and Alpha the alligator is standing in an elevator. You can see him here sitting on the elevator. Now, the elevator is attached to a string, but for all intents and purposes, he's in a black box. You can't see out. He doesn't know anything, but he is standing on a scale. Okay, now, why is it important that he's standing on a scale? It's important that he's standing on a scale so we can quantify the sensations that he's feeling and be able to take some measurements. So remember that the scale reading that you get, so scale reading equals the normal force. We learned that in our last lessons, and I can't reiterate enough how important it is to understand that if I ask what the scale reading is, what I'm really asking you for is what is the normal force acting on the object, because that is what's accelerating him. The elevator is attached to the scale. The scale is what's actually pushing him up, but the scale is being accelerated by the elevator, and the elevator is being accelerated by the rope, the tension in the rope. And that's being, it just goes on and on all the way down, back down to the earth. But for what we're doing now, just remember, scale reading equals the normal force. Now, this alligator has a small mass of just 120 kilograms. Not that it really matters. We can do these questions without any values whatsoever, but we're going to do this. Calculate the reading on the scale, the normal force, when the elevator is at rest. So the very simple starting point, the elevator is at rest. Now, if it's at rest, we're assuming that it is not accelerating as well. So there's no acceleration. So if we were to draw this here, we know that for sure, we know there's mg pulling down the weight of the alligator. He is in contact with the surface. So I draw that just to help me remind me that, okay, he is touching a surface. And there must be a normal force upwards. Now, that normal force upwards and the weight pulling down, if you're not accelerating, we know they're balanced. It's that simple. Because there's no acceleration, Newton's second law says this is 0. So the net force is 0. And the reading on the scale, so I'm just going to choose up positive for all these questions. It's Fn minus mg equals 0. So the normal force is equal to the weight in this very specific case. So it's equal to the weight. And if you ask the elevator, if you ask the alligator, either one, I guess, is the same result. What he would experience, you would just say, well, okay, I'm standing here. That's all that's happening. I'm at rest. I am not accelerating, and therefore the reading on the scale matches exactly what I normally weigh. And so that is the balancing force because there's no acceleration up, and the system is not accelerating down. Plugging in some numbers for this, it's just 120. I'm just going to use 10 to make life easy for this. So just for these examples, I'm just going to use the acceleration of gravity as 10 meters per second, just so the math's a little bit simpler. So that's just 1,200 newtons of force. Okay. So you would measure 1,200 newtons on the scale. Okay. Or, if you want to use 9.8, use 9.8. Calculate the reading on the scale when the elevator is moving upwards at a constant speed. Well, what does constant speed mean? It means no acceleration. If it means no acceleration, then the forces are balanced. And so the net force is 0. They're balanced. And you're like, well, how can that be? I don't understand what's happening. If you're moving upwards, it doesn't matter if you're going upwards at 10,000 kilometers an hour. If you're not accelerating, meaning you're just staying at 10,000 kilometers an hour, then literally the force of gravity pulling down on you and the normal force have to be balanced because you are not accelerating. upwards or downwards. And so you wouldn't even know you were moving. If this elevator was completely smooth, you were knocked out, woke up inside this elevator, and it all of a sudden had gone through the accelerated phase. It does have to accelerate to that speed. So during the accelerated phase, you're going to notice that you're accelerating. But once it reaches its constant speed, just like when you're in a car, your inertia says, well, I'm moving upwards. I'm just going to keep moving upwards. And so therefore, the force that's balancing out your motion upwards and your weight are going to balance. And it's really just your inertia, the 10,000 kilometers an hour upwards, that you maintain. And so therefore, you would notice no difference. So once again, the same. You would feel the same. Okay. Now let's look at another case. Now we're saying that calculate the reading on the scale when the elevator is moving downward at a constant speed. 95% of people would say, oh yeah, you're going to appear lighter. You're going to seem lighter. You're going to feel like you're floating. No, not right. It's wrong. During the accelerated phase downward, yes, you're going to feel that, but not during the moment when you're moving at a constant speed. Use the physics. Believe what it says. Your acceleration is zero if you're moving at a constant speed. So therefore, what does that mean? Well, that means the net force is zero because it's balanced. The only way you get acceleration is if the forces aren't balanced. So that means that your normal force upwards and the weight pulling you down, the force of gravity, there's my surface. Doesn't matter which way. I can even just choose down as positive now. It doesn't matter. You'll get mg minus Fn equals 0. Same result anyways. Fn equals mg. So Fn is still 1200 newtons. The same. So it doesn't matter whether you're at rest, moving upwards at a constant speed, or moving downwards at a constant speed. The force reading on the scale, or the normal force, which is what it's measuring, are the same. Getting to those points, of course, you've got acceleration up, acceleration down. You're going to notice things, but not when you're moving at a constant speed. So if this guy was moving down at 10,000 kilometers an hour, he would just be like, well, I'm either moving upwards at a constant speed, I'm moving downwards at a constant speed, or I'm stationary. You wouldn't be able to tell if he was in a completely contained elevator and he was out cold during the accelerated phase. There's no way to tell. Just like on the Earth, we don't realize that we're moving at tens of thousands of kilometers an hour around the sun. We don't notice it, right? We don't even notice that we're rotating because of inertia and because of the fact that we're accelerating very little. Okay. The reason why you can tell you're moving in most elevators is because there is accelerations constantly. There's friction, there's vibrations, there's sound, all those things that give away the fact inside your body that you're accelerating and changing speed and changing motion and changing position. But there are instances where you could make this perfectly impossible to tell. Okay, so let's take a look at the next one, D. In this one, calculate the reading on the scale when the elevator is accelerating upwards at a rate of 3 meters per second. So now there's acceleration. In fact, it's accelerating upwards. So we make that direction positive. That means that the normal force must be larger than the weight. Otherwise, you're not going to accelerate. So we use Newton's second law. And we write it as Fn minus mg equals ma. It's not equal to 0 anymore. And we bring them over. So here's our normal force. It's m. In fact, this is your general formula right here. A plus g, if you're moving up and a is positive, you're going to be getting a greater normal force. So it's 120 times 3 plus 10. Right? So that's 13. Was it 3? Yeah, 13 times 120 your normal force would be now 1,560 newtons. So it would be larger during an upward acceleration. Well, watch this. I think you can get the idea. By now, you probably don't even need to watch the tutorial. You can just figure it out, but figure it out to the end. Calculate the reading on the scale when you're accelerating downwards. Well, now the weight doesn't change. It's still just mg, still 1,200 newtons. But your normal force is better be smaller because you're now accelerating this way. And your normal force will show up accordingly. So we just follow the physics. Bring it over. Change the signs. And the last step, I just to make it look a little bit nicer, I'm going to write it as m g minus a, because that's g, positive g minus a in common factor, and there we go. Notice what happens here. G minus a is going to be a smaller number, so your normal force should be smaller. So 7 times 120. No, 7, yeah. 10 minus 3 is 7. 7 times 120 is 840 newtons. Smaller. We could have actually just gone up here before and looked at it and said, oh, in the second problem, make the acceleration negative. Negative 3 plus 10 is 7. 7 times 120 is 840. So we could have just used the same formula up here, but just realized that our acceleration was backwards. It was pointing in the wrong direction. So we just switched the acceleration to negative. Or you can just redraw the diagram, point the acceleration in the correct direction, and you realize that your normal force must be smaller than the weight of the object. The faster you accelerate down, the lighter you're going to feel. If you're in an elevator and the elevator snaps, you're going to feel weightless, just like when you're in orbit. And the reason you're going to feel weightless is because there's no more normal force. And so here it says calculate. Well, it's one of the questions you can do later where if you cut the cord and the thing started to drop at 9.8, if you look at your formula here, if you go into free fall, if you use 10 meters per second minus, and you're in free fall 10 meters per second, you get 0. 0 times anything is 0. Your normal force would be 0, and you would be floating in the floating in the elevator, just like everything else would be floating in the elevator, which is the exact same thing that happens when you're in orbit around the Earth and you're in a spaceship, right? There's lots of gravity up there, but you are in constant free fall, and therefore, since you're accelerating at the same rate of gravity up there, when they subtract each other, you get 0, and there's no normal force, and you're floating or appearing to float. All right, it says calculate the acceleration in the elevator if the reading on the scale is 165. So we draw a little thing. We know his weight is 1,200 newtons, and it says the reading on the scale is 65, so it's smaller. That's his normal force. Which way is he accelerating? Clearly downward, because it's an unbalanced force. Sigma F equals ma, mg minus Fn equals ma, and therefore the acceleration is mg minus Fn over the mass. 1,200 less 65 divided by 120. And you end up with 1,200 less 65 divided by 120, 9.5. It's almost a rate of acceleration. You would feel pretty sick in this situation. Almost full G. Right? If it was 9.8, you'd be in free fall. Here, you're almost in free fall. You'd feel pretty sick. You'd be like, oh man, I'm definitely floating off the ground here a little bit, or just about to lose contact. And the same thing, if ever, so there's some summary pieces here, right? And the summary is pretty nice. If Fn is greater than mg, you are accelerating upward. But get ready for this. This is when your mind maybe is going to have a little bit of an upset feeling. If the normal force is bigger than gravity, you're accelerating upwards. This could mean that you're moving up and speeding up, or you're moving down and slowing down. Take a minute to think about that. If the Fn is bigger than mg, you have to be accelerating upwards. That means that you could be moving upwards and speeding up, or you could be moving downwards and slowing down, or stationary. Stationary and moving, like you're either stationary, moving up and speeding up, or you're moving down and slowing down. If Fn is less than mg, you are accelerating down. You may have to write this on a separate sheet of paper. I kind of really ran out of space here. You're accelerating down. So you could be stationary or moving down and speeding up, or you are moving up and slowing down. So if Fn is less than mg, you have to be accelerating downwards. You could have been stationary, or you could have been moving down and then just speeding up. So you're going to notice that you're accelerating down. Or you could be moving upwards, but slowing down. So if you've ever been in an elevator that's moving up really quick and it slows to a stop, you're like, whoa, you get that sick feeling of like you're moving. Well, that's just inertia. Your body is moving upwards. So if the elevator slows down underneath you, you're going to feel lighter and you're going to get that sensation because you're trying to keep moving in the straight line upwards, but the object that you're in is slowing down or is decelerating. Same thing if it's moving downwards and starts to speed up, your body was already at one speed. It doesn't want to go to the next speed. So it has to speed up to catch up. And that acceleration is what you sense as this sort of floaty feeling in your stomach. The opposite happens with the Fn greater than mg. When Fn is greater than mg, you are going to feel pushed into the elevator, whether you're accelerating up, whether you're moving up and speeding up or moving down and slowing down. In either case, you are going to feel heavier. And you're going to feel that push because of inertia. Your body's trying to stay in motion in either direction. The last one, if Fn equals mg, you are moving at a constant speed or stationary. You don't know which one. You're just one or the other. You're either moving at a constant speed up or down, or you are stationary. And it's not until you accelerate that you would know which situation you're in. If you start to get heavier or feel heavier, you know you're accelerating up. If you know you were stationary, you know you're moving up. If you don't know if you were stationary, then you don't know if you were moving up and speeding up or moving down or slowing down. It's really that complicated. It is quite a weird thing. Most often, because you get to elevators, you know which of these two cases you're in because you know what the elevator's doing. But if somebody, if you fell asleep in an elevator and it was some weird elevator in some weird place in the universe and it could accelerate up and down and do whatever it wants, and you woke up in it and you felt heavier, you would have no idea which of these three cases you were in, whether you were stationary, moving up and speeding up. So whether you were stationary or moving up and speeding up, or whether you were moving down and slowing down, you wouldn't be able to tell. Same thing with the other cases. This is probably the most important part of this entire lesson right here. I'm glad I saved such a small little space for it. Okay, there's another video you can watch on this that I suggest you watch. I think it's from the Khan Academy, and it talks about this as well. Okay, so now you can finish up the questions from the previous assignment about elevators and elevator type questions.